You can go ahead, ma'am.
Okay.
Thank you.
Thank you, sir. Hello and good evening. Welcome to today's session on solving differential equations using MATLAB. My name is Priyanka Shukla and I work for MathWorks. So the agenda for today's session is, first we'll start with a brief overview of MATLAB, and then we will see what all will be covered in today's session. MathWorks is the leading developer of mathematical computing software for engineers and scientists. Our tools are being extensively used in various industries such as aerospace and defense, automotive, biological sciences, financial
I
services,
need my
medical
sister.
devices, to name a few. I request all the participants to mute themselves. Thank you. So the agenda for today's session is, we will start with a recap of differential equations and their types. We will also briefly discuss what are the various MATLAB ODE solvers. Then we will talk about the problem statement for this session and its solution. We will have a hands-on activity to see how we can solve the problem statement for this session. And then we will conclude the session by summarizing it, followed by a quick Q&A session to answer any questions you have. So differential equations can be defined as a mathematical equation that involves an unknown function and its derivatives. It describes the quantity changes with respect to one or more independent variables. There are various applications of differential equations. It can be used to model real-world phenomena or predict any system behavior, or it can be used to optimize and design the engineering systems. Differential equations can be classified in various ways. One such way is based on the order. So first order equation involves the first derivative, for example, the velocity. If we talk about the second order equation, then it involves acceleration, such as a spring mass system. Next, based on the linearity, we can divide the differential equations as linear and non-linear. So linear equations are simple relationships like the RC circuits. For non-linear equations, we have systems such as population growth or predator-prey models. We can also classify differential equations based on the homogeneity. By homogeneous equations, we mean that there are no external inputs, while we also have the non-homogeneous equations, which include forcing terms such as applied voltage or external load. Finally, we can also classify the differential equations based on the derivatives. So we have two types here: ordinary differential equations, which depend on one variable, usually time. We also have the partial differential equations, which depend on multiple variables, like heat distribution in space and time. So this classification helps us to choose the right modeling approach and the solver configurations. So let's take a look at the various MATLAB ODE solvers that are available. So MATLAB offers a different ODE solvers, which is suited for different type of problems. There is no single solver that will work best for all the cases. The most commonly used ODE solver is the ODE45. It is used for a good starting point for any non-stiff problem. So when I say non-stiff problem, we mean systems where the solution changes smoothly and gradually over time. If the problem is simple and speed matters more than accuracy, then we can also go for ODE23. If we talk about the non-stiff problem, that means problems that require higher accuracy, then ODE113 is a good choice. But what happens when the system is stiff? So by a stiff system, we means that the system contains multiple time scales. Some parts of the system change very fast, while others change very slowly. So in such cases, solvers like ODE 15S, ODE 23S, ODE 23T, or ODE 23TB, they are more appropriate. So these solvers handle the systems with fast and slow dynamics more efficiently. So in practice, we generally start with the ODE 45. If it becomes slow or unstable, we switch to a more stiff solver. So in today's session, we will be talking about ODE 45, ODE 15S, and ODE 23S. So let's talk about what we are going to do in today's session. So in many biological and bioengineering systems, two interactive populations influence each other's growth. One classic example is the predator-prey model, where the prey population will grow in absence of the predator, while the predator population depends upon the availability of the prey for survival and reproduction. So in this session, we will see how a simplified predator-prey interaction using a system of first-order differential equations known as the Lotka-Volterra model. You will use MATLAB to simulate the system, compare the different numerical solvers, explore how different initial population level affects the system behavior, and then finally analyze how sensitive the model is to its parameters. So now let's go to the next part of the tutorial where we'll be practicing solving the differential equations using MATLAB. So for this purpose, I will share a work live script which has placeholder codes. During the session, I will post the relevant codes in the chat window so that it is easier to follow along with me. At the end of the session, I will share the solution live script, which you can use for your future references. So to get started with the hands-on activity, I will share the work live script. Please go ahead and download the work live script. So I have shared the work live script in the chat. Please download this work live script so that you can follow along with me during the hands-on session. I hope you have downloaded the live script. So to access the MATLAB, go to the NPTEL course page, and in the course outline section, come down to MATLAB and then click on MATLAB. I repeat, to access MATLAB online, please go to the NPTEL course page. In the course outline section, come down to the MATLAB and then click on it. So you will see two options there. One is MATLAB Access and other is MATLAB Training. Click on MATLAB Access and then you will have a series of steps mentioned. If you have already accessed MATLAB online, provided with the course, you can directly proceed to step 3 and click on the link that is provided there. If you have never accessed the MATLAB online provided with the course, please follow the steps 1 to 3 to access the MATLAB online. Once you click on the link 3, on the link that is provided in the step 3, this will take you to the MATLAB online page. So you will see something similar to what I'm sharing on the screen. The URL will be matlab.mathworks.com. Once you reach there, click on MATLAB online button. This will take you to the MATLAB online. I repeat, once you reach this page of matlab.mathworks.com, click on the Open MATLAB Online button to take you to MATLAB Online. So after that, you can see a MATLAB Online window. On the right, on the left side, you will see the Files section. So right click here so that you can select to upload the files here. Once you right click to upload the files, you will see a window which shows open, and then navigate to the download section where you have just downloaded the work live script. And then after selecting the work live script, click open to upload the live script to the MATLAB drive. Once you have clicked on open, you will see that there is a upload files dialog box, and it will show that the upload is 100%. You can click OK on this so that the live script gets uploaded to the MATLAB drive. Now you will come back to the MATLAB Online, and in the files section, scroll down so that you can see work underscore live script underscore csv.mlx that you had just uploaded to the MATLAB drive. Double click on this live script so that it opens up in MATLAB Online. I hope you all were able to follow along with me. So once you have uh, clicked on work underscore live script underscore csv.mlx, you will see a live script. So we will start with the solution for the problem statement. So the first step is to solve the predator pre-model using the different ODE solvers. So first of all, we will consider that a pair of first order differential equations known as the Lotka-Volterra equations or the predator pre-model. And we are defining them using two equations, that is dx by dt is equal to x minus alpha xy, and dy by dt is equal to minus y plus beta xy. The variables x and y measure the sizes of the prey and the predator population. Alpha and beta are the interaction strengths. So whenever the prey population is increasing when no predators are present, and the predator population will decrease when the prey are very less. So these equations describe a coupled non-linear system. And now we will see how we can solve this using MATLAB. So first of all, we have to create an ODE functions. So all MATLAB ODE solvers expect the system to be in a standard vector format. So for this purpose, we will define the function. Function dy dt is equal to Lotka with the arguments of t, y, alpha, and beta. I will simultaneously be posting the codes in the chat so that it is easier for you to follow along with me. So first, we are defining the predator prey model. So for that, to compute the derivatives of the predator prey-like interactions, we will define x and y, and then dx dt and dp dt, so that all the arguments that are there for the function are defined. So first of all, we will define x as x is equal to y of 1 . I will also post it in the chat so that you can easily follow along with me. After defining x, we are going to define p, which is equal to y of 2. After this, we are writing the equations. So dx dt, which is equal to x minus alpha into x into p. So to define the differential equations, we are using dx dt is equal to x minus alpha into x into p. Now we will define the second equation with the variable beta. So dp dt is equal to minus p plus beta into x into p. And then we are defining the final function dy dt is equal to dx dt semicolon dp dt. So now we have defined the function for the MATLAB ODE solver. So we'll go ahead and run this particular section. So at this point, we have a reusable ODE function that will fully define the predator pre-dynamics. Next, we will specify the parameters and the starting conditions for the simulation. So we will specify alpha, beta, the interaction strengths, the initial population Y naught, the simulation duration, that is T span, and the solver tolerances for numerical accuracy. So we will be solving the predator pre-model using ODE 23, ODE 45, and ODE 15S. So for that, first let's define the parameters alpha and beta. So alpha is equal to 0.01 and beta is equal to 0.02. Next, let's define the initial conditions and the time span. So the initial condition Y naught is equal to, we will be mentioning the predator and the prey, both predator as well as prey initial condition. So we are assuming that both predator and prey are having the initial condition of 20. So Y naught is equal to 20 semicolon 20. So here we are defining both the prey as well as predator initial condition. Next, we will define the time span. That is the simulation time. So here we are using the variable T span to define the uh, simulation time, and we will simulate the system for 15 seconds. So T span is equal to 0 to 15. Next, we will define the solver option. So for this, we have used the variable OPTS. So OPTS is equal to ODE set, and where we are talking about the relative tolerance and the absolute tolerance for this system. So once you have added the codes in the placeholder for the codes, we can go ahead and run this particular section. So now we will solve the same ODE using 3 different MATLAB solvers. This will help us to isolate the effect of the solver choice. So we are using ODE 23, which is a lower order and more suitable for variable step. Then ODE 45, which is a general purpose default solver. And then we'll also use ODE 15S, which is designed for stiff systems. So let us write the code to solve the system using ODE 23. Next, we will write the equation to call the solver using ODE 45. And then finally, we'll write the equation to solve using ODE 15S, which is a stiff solver. So once you have added all the equations, codes of for the equations, we can go ahead and run this particular section. We can run the section. So we will be comparing the results visually. And for this, we are going to use a population and time plot. So this will help us to see whether the different solvers predict the same time evolution. So using the plot, you observe. So for that, first of all, we'll go ahead and run this particular section. You can see the plots on the right side of the live script. So from the plots, you can observe that. So you can observe that the overall trends are similar, and we are also using the same phase plane plot. So this will remove the time and show the relationship between the predator prey populations directly. So the phase plot highlights the system behavior is independent of the solver time setting. So from both the plots, we can see that all the solvers produce consistent system behavior. So now that we know the predator pre-model solution is numerically consistent across the solvers, the next engineering question for us is how does the system behave under different starting conditions? So this will lead us to step 2 directly, where we will solve the same ODE system for multiple set of initial conditions and compare the resulting population trajectories. For this purpose, we will now explore how the same system behaves when we change the starting populations. This is very important because for nonlinear systems, the initial conditions can significantly affect the system trajectory, even when the systems remain the same. So we are going to use the same model, the predator-prey model that we have used before, and the same numerical solver. This will ensure that any differences that we observe now will come only from the changes in the initial conditions. So let us add the equation. So we already have a function defined here, that is dp dt. So now for this, we will define the delta and the beta values here. So delta can be defined as delta is equal to 0.02 and beta is equal to 0.01. So you can write a delta is equal to 0.02 and beta is equal to 0.01. So once you have entered the values for delta and beta, you can go ahead and run this particular section. So now we have two equations in the system, and dp dt is a vector with one element for each equation. The solution vector P has only one element for each solution component, P of 1, which represents X in the original equation, and P of 2, which represents Y in the original equations. So we will keep the time interval same as 0 to 15, and we will set the initial population size for X and Y to be 50. So once we have added these values, we can go ahead and run this particular section. So now we will solve the system using ODE 45 by specifying the ODE function, the time span, and the initial condition. So ODE 45, it will integrate the system over time, and then we will plot the resulting population versus time. So to solve this, let's add the ODE system, which is over T naught and T final. So T comma P is defined by ODE 45 with the function of Lotka ODE, and the time is from T naught to T final for the population P naught. So once you have added this, go ahead and run this section so that we can see the plots which show how each population evolves over time for this specific starting point. So here we can observe the effect of how each of the population is evolving with the time when the starting point or the initial state is different. So the initial prey and the predator populations were given as 50 each. So we see that the solutions exhibit periodicity and plot the solutions against each other. So let us also now plot the phase trajectory. So this will see how close the trajectory is phase space for a single initial condition. So we'll go ahead and run this particular section. So from the resulting plots, we can see that the solution for the given initial population sizes. So to solve the equations for the different initial population sizes, change the values in P naught and then rerun the simulation. However, this particular method can solve the equations for only one initial condition at a given time. Solving the system for just one initial condition does not tell us how the system behaves more generally. What happens if we start with fewer predators or we have more predators? To answer that, what we need is we need a more systematic way to simulate multiple initial conditions. So in the next section, we will see how to solve a differential equation system for different initial conditions. So for this purpose, we are going to use a for loop. For this example, we will have the initial population size for X to be constant at 50. And then we will use the for loop to vary the initial population size for Y between 10 to 400. So this will help to create a vector of the population sizes for Y naught, and then loop over the values to solve the equations for each set of initial condition. For each iteration, one trajectory will be produced in the phase space. So by the end of the for loop, we will have simulated multiple starting conditions. We will also plot the phase plot with each result for all the iterations. So let us add the equation. So we will be initializing Y from 10 to 400 with a step size of 10. So let us define Y naught to be Y naught is equal to from 10 to 400 with a step size of 10. So once you have added this initial condition for Y naught, go ahead and run this particular section. So from the phase plot, you can see all the computed solutions for the different sets of initial condition. So this phase plot has overlaying trajectories for many different initial conditions. You can also observe that the trajectories form a closed orbit. Their shape is similar, but the size of the plot depends upon their starting population. So this means that the predator-prey system exhibits a structured and repeatable behavior across a different multiple initial conditions. So this tells us that the qualitative dynamics for the are robust to changes in the initial populations. So the major key takeaway here from this second step is that while the exact trajectory depends upon the initial population, the overall system behavior remains consistent throughout. So this prepares us to analyze the stability, equilibrium, or other qualitative properties in the next step. So in the step 3, we are going to perform the sensitivity analysis for the model parameters. So here we are trying to answer a more specific engineering question, that is, how sensitive is the system behavior to uncertainty in the model parameters? You can ask like why this engineering problem affects us or why it matters to us. So it is important because in real systems, parameters like interaction rates are never known exactly. So what we will do is we will first define a baseline, a set of parameters and initial conditions. And then all the sensitivity results will be compared against this baseline. So this baseline solution will act as a reference point. So first, let us add the values for alpha naught and beta naught so that we can define our baseline solution. So alpha naught is defined as alpha naught is equal to 0.01 and beta naught is defined as 0.02. After that, we are going to define the initial population for predator and prey. So we are going to use the same initial condition for both predator and prey. So y naught is equal to uh, 20 for each prey and predator. So this is the initial condition for both the prey and the predator population. The t-span that we are going to use is the from 0 to 15. That means we are going to simulate our system from 0 to 15 seconds. And then let us define the ODE function and the relative tolerance and the absolute tolerance. So the relative tolerance is 1 e to the power minus 6 and the absolute tolerance is of e to the power minus 9. So once we have defined the baseline solution, which will act as a reference point, go ahead and run this particular section. So now after we have defined our baseline solution, we will now define the we will now solve the model using these baseline parameters. This will represent our best estimate for the system behavior. And we will now have a reference trajectory against which we will compare the results. So we are defining it as using the variables t underscore base and y underscore base. So t underscore base comma y underscore base is equal to ODE 45 with the arguments t and y, and then Lotka with the arguments ty, alpha naught, beta naught, and the t span that we had defined, the initial population, and the relative and the absolute tolerance that we had defined. So once you have added this equation, go ahead and run this particular section. Now next, we will introduce a small control changes to the parameters. We will change one parameter at a time and compare the results and define it with a change of plus minus 10. So this will help us to isolate the effect for each parameter. So we will define delta is equal to 0.1 0, that means the 10%. So we have defined a perturbation or changes of 10%. After that, go ahead and run this particular section. So now what we will do is we will test the parameter sensitivity. So first we are going to examine the sensitivity to alpha, which controls how strongly the predators will suppress the prey. So go ahead and run the next section, which will help us to see a plot of the predator population time series for multiple alpha perturbations. So you can observe that there are changes in the oscillation amplitude and also changes in timing. So even if there is a small change in alpha, there is a noticeable difference in the system dynamics. This tells us that alpha or the predator-prey interaction strength is a critical parameter for this particular system. Next, we will repeat the same process for beta, which governs how efficiently the predators grow when prey is available. So for this, go ahead and run this particular section. This will help us to see the sensitivity for parameter B. So we can see the effect on the predator peak values and also on the comparison with the baseline. So this shows that the predator growth efficiency shapes the population dynamics. From both these sensitivity plots, we can draw three important conclusions. One, the small parameter changes can lead to visibly different trajectory. Second, if we are using different parameters, they will have they will influence different aspects of the dynamics. And third, even if we are having the identical conditions, uncertainty in parameter still matters. So to conclude this session, we studied the predator-prey system using MATLAB ODE solvers, and we have seen how different numerical solvers are producing consistent solutions for the same model. We also explored how changing the initial conditions affected the system. And finally, we demonstrated how uncertainty in model parameters can significantly influence the system behavior. So I have added a section for additional resources, which includes MATLAB documentation and further reading pages for deeper exploration. Now I will share the solution live script, which you can refer to for your future references. So to conclude this session, we have seen how MATLAB ODE solvers were used to solve the predator-prey system. We compared the solver behavior and the solution trends. We also saw the impact of initial conditions and parameters on the system behavior. We also demonstrated a practical end-to-end ODE modeling workflow. Thank you for attending this session. If you have any questions, you can post them in the chat. It seems there are no questions. Thank you everyone for attending today's session. Thank you, sir, for coordinating this session. You can close the session now. Yes, I can share the solution script again. 1 second.
Looks like there are no more questions. Thanks, Priyanka. Thank you.
Thank you. Thank you, Prithvi. Thank you, sir. Thank you, everyone.